Welcome to Tejasri Electrical Engineering YouTube channel. In this video, we will learn about the subject electrical measurements part A, chapter 1 error analysis. The definition of error. The deviation of measured quantity AM from true or actual quantity AT is called error. Error equal to measured quantity minus true value. Types of errors. There are two types of errors, static error and dynamic error. Static error is nothing but the error. The deviation of measured quantity from true or actual quantity is called also static error. The static error is independent of time. Static error is nothing but absolute error. Absolute error equal to measured quantity minus true value. If measured quantity is greater than true value, this type of error is called positive static error. If measured quantity is less than true value, this type of error is called negative static error. Next, dynamic error. It is the difference between true value of the variable to be measured changing with time and the value indicated by the measurement system at zero static error. Next, correction factor. Correction factor is the value which is add or subtract from the measured quantity to get actual or true value is called correction factor. Correction factor is the value which is add or subtract from the measured quantity to get actual value is called correction factor. Correction factor equal to minus of measured quantity minus true value. It is nothing but static error. Correction factor equal to minus of static error. Correction factor may be positive or negative. Next, relative static error. The ratio of absolute error to true value is called relative static error. Relative static error is nothing but error by true value. Measured quantity minus true value by true value is called relative static error. Percentage of relative static error equal to measured quantity minus true value by true value into 100. Here absolute error is nothing but measured quantity minus true value. This 10 relative static error indicates the quality of instruments. For example, instrument A and instrument B have measuring the true value of 2 amperes and 1000 amperes respectively. Error in instrument A 1 ampere, instrument B 10 amperes. Then relative static error equal to error by true value into 100. Instrument A has 50% of relative static error. Here instrument B error by true value into 100. Instrument B has 1%. That means instrument B is good instrument compared with instrument A. Percentage of error is low here. Next, the important term, limiting error. The limiting error will be specifies the range of operation. This error is specified by the manufacturer at manufacturing time by the company. The percentage limiting error is always with respect to true value. Sometimes this limiting error is also called tolerance or uncertainty. The percentage of limiting error equal to absolute error by true value into 100. That means the percentage of limiting error is specified in terms of true value. The basic characteristics of and measuring instrument. The basic characteristics of and measuring instrument are classified into two types. They are static characteristics and dynamic characteristics. Accuracy, precision, linearity, sensitivity, hysteresis, reproducibility, repeatability, drift, threshold value, resolution. These all are called static characteristics of an measuring instrument. Next, another one, dynamic characteristics. Response time, speed of response, dynamic error, fidelity, measurement lag, dead zone. These are called dynamic characteristics of an measuring instrument. We have to discuss about the static characteristics of an measuring instrument one by one. Number 1, accuracy. Accuracy indicates the degree of closeness of measured value to true value. Accuracy indicates the degree of closeness of measured value to true value. How much of measured quantity is closer to the true value is called accuracy. This accuracy may be specified in terms of inaccuracy or limits of errors. And accuracy can be expressed in the following ways. The accuracy is specified in terms of point accuracy. Means the accuracy is specified 0 to over a 0 to full scale range. It is specified at a point in the scale. Next, second one, the accuracy is specified in terms of percentage of scale range. Accuracy is specified percentage of scale range. Next, another one, accuracy as percentage of true value. The accuracy of an instrument is specified in terms of percentage of true value. Next, guaranteed accuracy error. This guaranteed accuracy error always specified in terms of full scale value. It is given by the manufacturer, hence it is constant error. Percentage of guaranteed accuracy error equal to absolute error by full scale value into 100. Measured quantity minus true value by full scale value into 100. We have to see the one example here. A 0 to 150 volts voltmeter has a guaranteed accuracy of 1% of full scale value. If the voltage measured by this instrument is 75 volts, then the limiting error in percentage is a 0 to 150 volts voltmeter has a guaranteed accuracy of 1% of full scale value. If the voltage measured by this instrument is 75 volts, then the percentage of limiting error is dash. See here, the voltage is 0 to 150 volts range, full scale value is 150 here, percentage of guaranteed accuracy is specified 1%. That means guaranteed accuracy error equal to absolute error by full scale value into 100 equal to 1. Then we have to get the absolute error here. Absolute error equal to 1.5 volts. Now the question required, the magnitude of voltage being measured is 75 volts. At this 75 volts, the percentage of limiting error is how much? The relative error at 75 volts is absolute error by, we have to need the relative error at 75 volts, then absolute error by 75 equal to 0.02. It is the relative error. Percentage of limiting error equal to relative error 75 volts at 75 volts by true value 75 volts into 100. We have to get 2%. That means we have to measure a 75 volts from a measuring instrument 0 to 150 volts voltmeter. That we have to get 75 plus or minus 2% or 75 plus or minus 1.5 volts. Next, the same instrument is measured for 1/3 of the full scale value. That means 37.5 volts. Then we have to get the relative error at 1/3 of the full scale value 37.5 volts is absolute error by true value means 37.5 volts. Then we have to get 0.04. It is the relative error at 1/3 of the full scale value. Percentage of limiting error equal to absolute error by error into 100. That means 4%. This 34.7%, 37.5 volts is written as 37.5 plus or minus 4% or 37.5 plus or minus 1.5 volts. From the above example, as the indicating pointer moves from 0 to full scale value, percentage of limiting error decreases and the guaranteed accuracy error is constant, because the percentage of limiting error is specified in terms of true value. A guaranteed accuracy error is specified in terms of full scale value. Therefore, that is guaranteed accuracy error is constant. It is decreasing from 0 to full scale value. Limiting error, guaranteed accuracy error and percentage of guaranteed accuracy error are constant throughout the pointer moves from 0 to full scale value. Therefore, percentage of guaranteed accuracy error is calculated with respect to full scale value. The percentage of limiting error is not constant from 0 to full scale value because it is specified in terms of true value and it is reduced at near the full scale value. Therefore, percentage of limiting error is specified in terms of true value. We have to prepare operating meters at near the full scale value because percentage of limiting error is reduces near the full scale value. Next, the important static characteristics is precision. Precision is defined as the most repeatable value or reproducible value out of set of record is called precision. Precision is defined as the most repeatable value or reproducible value out of set of record is called as precision. For example, here the true value of current is 2 amperes and it record on two different ammeters A and B as follows. Ammeter A 6 readings recorded like this. Ammeter B recorded 6 times 6 readings like this. From these readings 1.9 amperes is near to the true value 3 times. Here 1.9 amperes near the true value 2 times. Therefore, precision of the ammeter A is greater than accuracy. The accuracy of ammeter A is greater compared with ammeter B. Here ammeter A records the 1.9 amperes 3 times. Here 1.5 amperes recorded 4 times, but it is not near to the true value. Precision is nothing but most repeatable value, that is 1.5 amperes 4 times. Here 1.9 amperes 3 times. That means the precision of instrument B is greater than instrument A. Ammeter A has high accurate and precision low when compared with ammeter B. Ammeter B has accuracy low but precision is high when compared with ammeter A. Here an important statement here. Accurate instrument may be precision instrument, but precision instrument may not confirm accuracy. Accurate instrument may be precision instruments, but precision instrument may not confirm accuracy. That means out of these 6 records here, 1.5 amperes getting 4 times. Sometimes due to the defective of the ammeter, we have to get again same values, but it is not the true near the true value. Therefore, we have to say that precision instruments not confirm the accuracy. We prefer always high accurate as well as high precision instruments. Next, the important static characteristics of an instrument is linearity. The output quantity of instrument follows the input quantity with linear relation is called linearity. If the input and output relation of instrument is linear, then the scale of the instrument is uniform. If the input and output relation of an instrument is non-linear, then the scale of the instrument is non-uniform. So here in graphically, if the input and output relation is linear, the scale is uniform throughout the 0 to full scale range. Here non-linear, then it is counted like this. In non-linear relation, the non-uniform scale, we have to select a meter in such a way that the pointer enters into the linear region of the scale. Linearity of instrument is desirable, but it is not a necessary condition. Next, the important static characteristics is sensitivity. It is defined as the ratio of the changes in the output of an instrument to a change in the value of the quantity being measured. It denotes the smallest change in measured variable to which the instrument responds. Deflection factor or inverse sensitivity is the reciprocal of sensitivity. For a linear scale, sensitivity is constant. Sensitivity is nothing but slope of the linear curve, tan delta equal to 1. For linear scale, sensitivity of the instrument is constant. We have not calculate for non-linear scales. It is not constant. Always prefer high sensitive instruments. Next, the important are static errors. Next, the important static characteristics is hysteresis error. Hysteresis error occurs when the value being measured is increasing or decreasing, and it might not be the same in both directions. For example, pressure. The increasing order of the pressure is represented like this curve A, and decreasing order of the pressure is represented curve B like this. If the instrument of the measuring pressure has only the reads positive values, the input of the meter is increased like this, but there is no output. This amount of input is called maximum input hysteresis. In decreasing of the pressure, if the input variable is 0, but it shows some output in the meter, that is called maximum output hysteresis. If the measuring instrument has capable of reading both sides, positive and negative, then the hysteresis curve is like this. This phenomenon, hysteresis, is results due to the presence of several factors such as mechanical friction, motion in bearings, magnetic effect, or thermal effect. Drift. Drift is an undesirable gradual shift or departure of output of an instrument over a period of time. Drift is an undesirable gradual shift or departure of the output of an instrument over a period of time. This shift is not related to input changes, operating conditions, or load. An instrument is said to have no drift if it reproduces same output readings at different times for same variation of input. Threshold value. If the instrument input is increased very gradually from 0, there will be some minimum value below which no output change can be detected. This minimum value defines the threshold value of the instrument. This phenomenon is due to input hysteresis. Next, the important characteristics: resolution. It is also known as discrimination. If the input is slowly increased from some arbitrary non-zero input value, it will again be found that output doesn't change at all until a certain increment is exceeded. This increment is called resolution of the instrument. Thus, the smallest increment in input, the quantity being measured, which can be detected with certainty by an instrument, is called resolution or discrimination. Here the difference between resolution and threshold value is: resolution defines the smallest measurable input change, threshold defines the smallest measurable input. Here resolution defines the smallest measurable input change, threshold defines the smallest measurable input. Okay. Types of errors: gross error, systematic error, random errors. Systematic error is again classified as instrumental error, environmental error, observational error. This instrumentation error is due to loading effect, misuse of instruments, inherent shortcomings of instruments. Gross error. The gross error occurs because of the human mistakes. For example, considering the person using the instrument takes the wrong readings, or they can record the incorrect data. Such type of errors comes under the gross error. This gross error can be avoided by taking the readings carefully. Next, random errors. The error which is caused by the sudden change in atmosphere condition. Such type of error is called random errors. This type of errors remains even after the removal of static error. There is no particular reason why error may be appear. It may be positive or negative. It's called random errors. It can be solved by mathematical tools like statistic analysis. We have to study later. Systematic error. The systematic errors are mainly classified into three types: instrumental errors, environmental errors, observational errors. Instrumentation errors. These are due to following reasons, three main reasons. Number one, inherent shortcomings of instruments. Such type of errors are inbuilt in measurements because of their mechanical structure. They may be due to manufacturing, calibration, or operation of the device. These errors may cause the errors to read true or too low readings. Next, misuse of instruments. The errors occurs in the instrument because of the fault of the operator. Next, due to loading effect. It is the most common type of error which is caused by an instrument in measurement work. For example, when the voltmeter is connected to the high resistance circuit, it gives a misleading reading, and when it is connected to the low resistance circuit, it gives the dependable reading. That means instrument resistance is also loaded on the circuit. The type of effect is called loading effect. This means the voltmeter has a loading effect on the total circuit. Next, environmental errors. These errors due to the external conditions of the measuring devices. Such type of errors mainly occurs due to the effect of temperature, pressure, humidity, dust, vibration, or because of the magnetic or static effects. Next, observational errors. Such type of errors are due to the wrong observation of the reading. There are many reasons for observational errors. For example, due to the incorrect positioning of the eyes while taking a reading on measuring scale. This error is called parallax error. Next, the important topic, statistical treatment of data. The random errors are caused by a large number of small effects, each one being a variable. The experimental data is obtained in two forms of tests. Number one, multi-sample test. In this, the readings are taken at different test conditions. Next, single sample test. The readings are taken at identical test conditions. When a number of multi-sample observations are experimentally, there is a scatter of the data about some central value. One method representing test results in the form of a histogram or frequency distribution curve. For example, number of observed readings versus length of a wire in mm is drawn. Here 99.7 mm is reads at one time, 92.8 mm is reads at 4 times, 100 mm is reads at 19 times. It is the central value. Next, 100.1 10 times, 100.3 mm 1 time. It is the central value. From the above histogram or frequency distribution curves, we have to calculate the number one, arithmetic mean. The most probable value of measured variable is the arithmetic mean of the number of readings taken. Arithmetic mean equal to x bar equal to number of readings, sum of the number of readings, x1, x2, x3, so on, xn by number of readings or samples, sum of the readings by number of readings. Here x bar equal to arithmetic mean, x1, x3, xn readings or samples. Here n equal to number of readings. Next, measurement of dispersion from the mean. The property which denotes the extent to which the values are dispersed above the central value is termed as dispersion. The other name for dispersion are spread or scatter. The samples are dispersed from central value. The range is called dispersion or spread or scatter. For example, here curve 1 x1 to x2 with a central value h, and curve 2 x3 to x4 with a central value h. From this we have to observe that curve x1 to x2 is very narrow and closer to the central value h. Therefore, it has high precision. Next, curve 2 x3 to x4, it is wide about the central value h. Therefore, it has low precision. The range. Simplest possible measure of dispersion is the range, which is difference between greatest and least value of data. Range of curve 1 x2 minus x1. Range of curve 2 x4 minus x3. Next, the important are deviation. Deviation is departure of the observed reading from arithmetic mean of the group of readings. The departure of the observed reading from arithmetic mean of group of readings is called deviation. Let the deviation of reading x1 be d1 and that of reading x2 be d2, like this. Then deviation of x1 equal to x1 reading minus arithmetic mean. Like this, d2 equal to x2 minus arithmetic mean. That means deviation equal to sum of the xn minus dn by dn, number of samples. Algebraic sum of deviations. We have to sum all the deviations d1 plus d2 plus d3, like this. d1 equal to x1 reading minus arithmetic mean, x2 minus arithmetic mean, x3 minus arithmetic mean. So like this, we have to summarize x1 plus x2 xn minus number of samples into arithmetic mean. It is equal to 0. That means sum of the all readings equal to number of samples into arithmetic mean. That means arithmetic sum of deviation is 0. Next, the important term, algebraic deviation. An indication of precision of instrument. Highly precise instrument yields a low average deviation between readings. The average deviation is defined as the sum of the absolute values of deviations divided by the number of readings. The absolute value of deviation is the value without respect to its sign. Average deviation d bar equal to, we have to, neglecting the sign, we have to sum up the deviations by number of samples is average deviation. Average deviation equal to sum of deviations by number of samples. Next, the important term and frequently asked questions in exams, standard deviation or root mean square deviation. Standard deviation sigma equal to square root of deviation 1 square plus d2 square d3 square plus dn square by number of samples. square root of sum of the deviation square by number of samples. It is valid for only greater than 20 samples. This equation is valid for number of samples is greater than 20. If the number of samples are less than 20, then standard deviation sigma equal to square root of sum of the deviation squared by number of samples minus 1. Next, the important term, variance. The variance is the mean square deviation, which is the same as standard deviation, except that square root is not extracted. That means variance equal to d1 square d2 square plus dc square plus dn square by number of samples. That means variance v equal to standard deviation square. Standard deviation square equal to d1 square plus d2 square dn square by number of samples. If number of samples are greater than 20, sum of the deviation square by n equal to variance. The variance, if the number of samples are less than 20, sum of the deviation square by n minus 1. From the above, probable error equal to 0.6745 standard deviation into sigma standard deviation. Standard deviation of mean equal to standard deviation by square root of number of samples. Standard deviation of standard deviation equal to standard deviation by square root of 2 times of number of samples. These calculations are very important for IAS examination in descriptive. We have to take in one example here. The following 10 observations were recorded when measuring a voltage. Sample 1, sample 2, sample 3, like this 10 observations. Find the mean, range, deviation, standard deviation, average deviation, variance, and probable error. Given data. The 10 readings are given, x1, x2, x3, x4, like this. First, number 1, arithmetic mean. Sum of the readings by number of samples. Here number of samples is less than 20. Number of observations is less than 20 and number of samples equal to 10. Arithmetic mean equal to sum of the readings by number of samples. We have to get 41.97 volts. Next, the important range. We have to take V max minus V average, V mean equal to A, V mean minus V minimum equal to B. Then the range of error equal to plus or minus A plus B by 2. For this example, this question, V max minus V mean 0.53, V mean minus V minimum 0.27. The range of error equal to 0.53 plus 0.27 by 2. We have to get plus or minus 0.4 volts. Next, deviation. The deviation is calculated per each term. D1 equal to x1 minus arithmetic mean. We have to get like this. D2 equal to x2 minus arithmetic mean. D3, D4, like this. The algebraic sum of deviations is equal to 0. We have to summation of all these deviations, then we have to get 0. Next, average deviation. Average deviation is nothing but the sum of the deviations by number of samples at The deviation value is taken irrespective of the sign. Okay, then we have to get 0.177 here. Next, the standard deviation. Here the number of samples are taken 10, that means less than 20. Standard deviation equal to square root of sum of the deviation square by number of samples minus 1. Calculate, we have to get the 0.2214. Next, variance. Here number of samples equal to 10, which is less than 20. Therefore, variance equal to sum of the deviation square by number of samples minus 1. That means variance is equal to standard deviation square. We are already calculated standard deviation 0.2214 square is nothing but variance. Next, probable error. Probable error equal to 0.6745 into standard deviation. We have to get 0.1493. Next, the important topic, frequently asked in GATE and IS. Uncertainty analysis. An uncertainty distribution is used for analysis of single sample test data. That means the data is taken at identical test conditions. If x is a function of several variables, x equal to f of x1, x2, x3, x4 and xn like this, where x1, x2, x3, xn are independent variables with the same degree of odds. Let wx be the resultant uncertainty. Wx is the resultant uncertainty, and wx1, wx2, wx3 and wxn be the uncertainties in the independent variables x1, x2, x3 and xn respectively. Then resultant uncertainty in function f of x equal to square root of dou x by dou x1 square into uncertainty in independent variable x1 square plus dou x by dou x2 into uncertainty in independent variable x2 whole square, so on, plus dou x by dou xn whole square into uncertainty in independent variable xn whole square. We have to see the one example here. A certain resistor has a voltage drop of 110.2 volts and a current of 5.3 amperes. The uncertainties in the measurements are plus or minus 0.2 volts, plus or minus 0.6 amperes respectively. Find the power dissipated in the resistor and the uncertainties in the power. In the above example, given data, voltage is 110.2 volts, current is 5.3 amperes, uncertainty in voltage is plus or minus 0.2, uncertainty in current equal to plus or minus 0.06. Then P equal to power equal to voltage in current. That means you have to get the total power as 584 watts. We have to deviation the power with the voltage, we have to get the current. That means 5.3. The same way, deviation of the differentiation of the power with respect to current, then get the voltage 110.2. Uncertainty in power, WP, resultant uncertainty in power equal to differentiation of P with respect to voltage whole square into uncertainty in voltage square plus differentiation of power with respect to current whole square into uncertainty in current whole square, whole root square. Calculate a simple example. We have to get the uncertainty in power. WP equal to plus or minus 6.7 watts plus or minus 6.7 watts. In percentage, uncertainty in power equal to plus or minus 6.7 watts by total power 584 into 100. Then we have to get the 1.15%. Next, the important topic: combination of quantities with limiting errors. When two or more quantities each having a limiting error are combined, it is advantageous to be able to compute the limiting error of the combinations. Sum of two quantities. If x1 equal to x1 plus x2, the relative increment of the function dx by x equal to relative increment d into x1 plus x2 by x. Dx by x equal to dx1 by x plus dx2 by x. Next, this equation is rewritten as dx by x equal to dx1 by x1 into x1 by x plus dx2 by x2 into x2 by x. We have to common all the x, all are cancelled out. x1 is cancelled, x2 is cancelled. Then we have to get absolute error in resultant combination equal to absolute error in x1 plus resultant absolute error in x2. That means we have to conclude that in case of addition and subtraction, the absolute errors are added. Next, the product of two quantities x equal to x1 into x2. Here we have to apply the log x equal to log x1 plus log x2. Differentiation with respect to x. We have to get 1 by x, 1 by x1 dx1 by dx plus 1 by x2 dx2 by dx. We have to rewritten this equation like this: dx by x equal to dx1 by x1 plus dx2 by x2. This means dx by x equal to relative static error or relative error, isn't it? In case of multiplication or division, the percentage errors are added up. We have to multiply with 100 here, 100 here, 100 here. Then we have to get the percentage of limiting error, resultant limiting error equal to percentage of limiting error in x1 plus percentage of limiting error in x2. That means we have to conclude that in case of multiplication and division, the percentage errors are added or relative static errors are added. We have to see one example here. A 3-phase power is measured by using 2 wattmeter method. Meter readings are: wattmeter A reads 50 watts with accuracy error of plus or minus 0.5% of its rating. Wattmeter B reads 125 watts with accuracy error of plus or minus 1.5% of its full scale value. That means 1.5% is the full scale value. In 1.5% of error is specified in full scale value. Plus or minus 0.5% of wattmeter A error is specified in terms of true value. Then both wattmeters full scale value is 150 watts. Then calculate the total power in the circuit. The above example given full scale value is 150 watts. Wattmeter 1 reads 50 watts with a accuracy error of plus or minus 0.5 percentage of its rating. That means 50 plus or minus 0.5% with respect to true value 50 watts. We have to get the 50 plus or minus 0.25 watts. Like this W2. This 125 watts with accuracy error of plus or minus 1.5% of full scale value. Guaranteed accuracy is 1.5% equal to plus or minus 1.5 by 100 into full scale. It specifies in terms of full scale value. Therefore, we have to get plus or minus 2.25 watts. Then W2 is written as 125 plus or minus 2.25 watts. Then the total power equal to W1 plus W2, sum of the two wattmeters, equal to 50 plus or minus 0.25 plus 125 plus or minus 2.25. In case of absolute errors in addition, these absolute errors are added up. In case of addition and subtraction, absolute errors are added. That means we have to get the 175, 125 plus 50 plus or minus 0.25 plus 2.25 means 2.5 watts. W total power W equal to 175 plus or minus 2.5 watts. In percentage, we have to get 175 plus or minus 2.5 by total power 175 into 100. That means 1.4285% the error. Thank you.